Okay, so we're going to have a quick look at a geometric argument that sine of cos of x is less than or equal to cos of sine of x. And we saw in the previous video that you only need to consider x between 0 and pi over 2. This is sufficient to show it for the remaining values of x. So we're only going to consider x in this range for our geometric argument. And what I'm going to do is consider, imagine you've got a unit quarter circle here, got an angle x, then we know that this length, height here, this is sine of x, and you also know that the width is cos of x. And you also know if it's a unit circle, you know that this arc length here is equal to x. We're working in radians. So now this is actually really helpful because if you imagine you've got this line of length sine of x, we're interested in cos of sine of x. So what we can do is we can project this outwards and then consider what happens where instead of having an arc length corresponding to our input of x, we've now got an arc length corresponding to our input of sine of x. You can see this is slightly less than x because if you take this whole blue line, you can see clearly this is shorter than this big curved line here. So you end up with slightly less. Sine of x is over here. And then it's really clear that cos of sine of x on this picture next to cos of x. So cos of sine of x is the width of this big blue line here. So you can already see that cos of sine of x is greater than or equal to cos of x, which was just this width here. So we've already shown that cos of x is less than or equal to cos of sine of x using a sort of proof by picture. So now, using a very similar idea, we're going to try and show that sine of cos of x is less than or equal to cos of x, which would show then sine cos of x is less than or equal to this, which is less than or equal to cos of sine of x, which is what we're trying to actually prove. So if we draw out another unit quarter circle here, imagine we've got our point on it, we've got our generic angle x between 0 and pi over 2, which means that the arc length here is x. And then we know that cos of x is the width here, this length is cos of x. And then what I want to do is, I'm interested in sine of cos of x, so I want to turn cos of x into an arc, and then I can have that as the arc length in place of x here. So imagine if you move this up to turn it into an arc, it's going to end up slightly higher up because this whole curved length here is going to be bigger than this line. You can see that from the picture. So if I now make this arc length here cos of x, I've moved slightly further up. And I want the arc length down in the bottom right corner just to make it really clear what's happening so it's familiar in terms of sine and cos. So if you imagine I take this whole thing, I reflect it, I'd perhaps reflect in the line y equals x if I was using those coordinates. So all I'm doing basically is I'm moving it so that our arc length cos of x is over here where we want it to be. And then you imagine the arc length is cos of x, this means this angle here is cos of x, a unit quarter circle. And then you know that sine of cos of x will be this height here. So this is sine of cos of x on this picture, and cos of x would be this length here. And then just to make it really clear, going back to the original picture, you can see now that sine of cos of x has to be this length here. So this is sine of cos of x is this length from here to here. You can see clearly this is shorter than the distance for cos x. And we saw previously as well that cos of sine of x, this was actually further down over here. So you're higher up for sine of cos of x, then you go down for cos x, and finally for cos of sine of x, you're lower down, so this is even bigger. So going using this proof by picture, you can conclude that sine of cos of x this is less than or equal to cos of x, which is less than or equal to cos of sine of x. So you can conclude sine of cos of x is less than or equal to cos of sine of x, using this nice proof by picture.